get this out of the way. Looks like it's streaming now. All right, so we're off to the races. Let me get me up there. All right, so what do we do? Oh, let's get this moved a little bit over here so I get more light. All right. Now, okay, so let's start with the screen share and see where we're at in the workbook. So we kind of were right around here, maybe. Nope, a little further. Sorry. Yeah, and so there it is, right there. So these were the definitions that we started with last time. And just to remind you, you could use those at any time. They're on page 21. All right, so 21 there. All right, and let me get rid of that for a sec. And so in practice, these words have all these arrows on them. And then we discussed last time that when we're doing the problems, we end up taking all the arrows off and just knowing that an I hat is there or a J hat if we're going up and down. So that is what we talked about down here. So we talked about these equations last time and how these are only valid if you have constant acceleration. And it turns out they're still extremely valuable because you can use coding to split up anything into small segments where acceleration is constant. We had to, I made sure you know that sometimes when I'm writing today, I might use V0x for the initial velocity or V initial x. Sometimes I usually use V final x, but sometimes I'll forget the final. If I do forget the final, that still implies final. And we're going to use delta x and x final minus x initial interchangeably. And as a result, let me maybe use a different color for this one right here. You could see that that means the equation sometimes looks like this or like this. Obviously, if you take this minus x initial and bring it to the other side, that's why it suddenly became positive. Now, a last piece that kind of came up in one of the problems, and it comes up in a lot of problems. I guess these two things here in the middle, maybe I should reorder them, but we're not doing that. All this information here we mentioned, be careful when an object reverses direction. If an object reverses direction, distance and displacement are not going to be related with a simple absolute value anymore. Similarly, average velocity and average speed, and I want to emphasize average, they're not going to be equal in magnitude anymore. And we also saw that we have to watch out for this stuff right here. In certain problems, sometimes acceleration could be a negative number, but you'd actually be speeding up. In fact, here is that case right here. If you were moving to the left, your velocity would be negative, less than 0. If your acceleration was also less than 0, your velocity would get more and more negative, which means speeding up. All right, so that's the tricky one that people have trouble with. When you're moving backwards, maybe consult this chart. All right, so that said, let's go look at a problem. Oh, finally, I know you're new students. This is the strategy. This is at the bottom of page 22, I believe. Yes, bottom of page 22. I know this seems crazy. I'm going to point this out. This is what I want to emphasize right now. Read, go through a bunch of crap, and then reread and make sure you know what you're doing. This is the classic physics thing to do, right? You read, you draw, get everything on your paper, get ready to go. And then before you start working, read the question one more time and make sure you know what you're trying to find. Make sure you know WTF, okay? Then, this is super critical in a physics class, do the problems algebraically. Later on, I won't be giving you any numbers. You have to do them algebraically. And you might be saying, why do this? Well, imagine if you want to make a computer code someday. You probably realize that, hey, computers are kind of a big deal now, right? This isn't 1902. So if you want to compute something in the real world, usually what you do is you try and line up your math and plug it into an Excel spreadsheet or a calculator or something, and you could set it up so that if you do the problem algebraically, each time somebody gives you different numbers, you could just hit enter and it will auto update and give you all the information you need. Or you could do a large number of cases for a wide variety of times or distances if you do things algebraically. So in practice, it's not that you couldn't just do everything by hand, but when you have to do the calculation 10 times, it's faster to learn how to do things algebraically than just have a computer do it all for you. So that's why we really want to do things algebraically, just being straight with you there, okay? All All right. We also get some extra ways to check your answer. It turns out if you do it algebraically, and that's like gold for an engineer, right? There's so few ways to check your work. It is nice to have that. All right. So let me get back there. That's my kind of motivation as to why we should care about this, I guess. Last time we started with this problem right here. So I'm going to let you either use the live stream for that or use the solutions for that. Again, you could use the last recording to get that problem. I want to maybe pick up with a different one just to mix it up. This looks like a good one. Let's try 2.1 here. All right. And if you've already done this problem, remember, you can work ahead on physics by just keep going along in the workbook. So what we're going to do today is first do one more of these with numbers. Then we're going to do one of these with algebra. And if time, then we're going to do one in the Y direction. So one more with numbers, one more horizontally with letters instead of numbers to get used to that. And then finally, we'll go into vertical motion. And yeah, it should finish us out today. Okay. So I'm going to draw this on my board. You've got it there. I'll fix up the whiteboard. It's not going to be perfectly aligned until I do the screen share. So I'm just looking at this. So number it 2.1. There's a car or some kind of block, and then it's going to crash into a wall. And so it says constant acceleration. Hey, that's cool. That means we can use our math. I'm just writing down the keywords from the problem that make me feel good here. It comes in at 35 meters per second. And it's going to stop in a distance of 9 meters. And that's all we know. Okay. So I'll get the whiteboard up here, make sure it's aligned right. Close enough. All right, so hopefully you could see that okay. So again, this is 2.1, and we're just going to kind of walk through this together. Now, if I look at my strategy, let's try and use this strategy and follow it, even though it probably seems boring at first. It will become ingrained in you. The first thing is read. I did that. The second thing is draw. I kind of did that already too. The third thing says label. I labeled some stuff on here. This is looking good. So it's not just enough to draw a little picture. You actually put some information that you know on there. Okay, cool. What's next? Identify the list of knowns and unknowns. Now, if you remember me last time, I told you, hey, we know that these are the things that show up in the equations. Okay. And again, if I'm too slow for you, or you think you know what you're doing, remember, you've always got the solutions. You could try and do it without the solutions and then just check there if I'm too slow. So, all right. But I'd rather go slowly because most people, this is their first time through this. Not everybody's had high school physics, right? That's the whole point of this class, is to help get you up to speed when you haven't had high school physics. All right. Now, in this case, the change in X, well, I could use my units to figure this out with no problem. I know that this is 9 meters. Well, meters is a distance. That's the only thing in this chart that it could possibly be. But I also know that's the distance it's traveled. Now, let me ask you something before we go on. Do you think this should be positive 9 meters or negative 9 meters? Because remember, all of these things could be positive. Well, not time. Time can't be negative. But the first 4 could be positive or negative. What do you think?
Positive?
Yeah. Don't we usually assume this, X is this way and Y is this way? Unless we're going to, do something weird, which you can in physics, right? There's no rule. You don't have to do this. But unless we're, unless we have something going to the left, why would we change our coordinate system? Sometimes you actually do that. Like if everything in a problem moves to the left, why not just call to the left positive, right? And it should work out. All right, so very good. Thank you for unmuting whoever that was. How about V initial X? Do we have a number for that?
35 meters per second.
Oh yeah, right there. So that's cool. So let's pop that in there. I like how you remembered to say the units. We should always think about that. What's V final X in this problem? Somebody else.
0.
Yep. And what was the key word in the problem that gave you that clue?
It stops in a distance of 9
Right on.
meters.
Yeah, it says time to stop, right? So very good. So that's what tells us that. And we don't even need units because 0 would still be 0. And then what's the acceleration? Do I know that?
Would it also be 0?
Does it tell us what the acceleration is? I just saw the typo there. Even thought the acceleration, whatever. We get the idea. It's not 0. And I could tell it's not 0 because remember, is the speed changing here or is the velocity changing?
Is it negative acceleration?
It should be a negative number because it goes from a positive velocity down to 0, right? But does anything in the problem give us the number directly?
No.
I don't see it.
Oh.
Yeah, but we do know it should be something and it should be negative, not 0. So let's just put a question mark here, meaning I don't know. That's something we could figure out. And G, I don't see anything about the time either, right? All of these problems have this pattern. You're always going to know 3 of these things and you figure out the other 2. So now how could we figure out this? In this case, we want to learn about A sub X and T, right? Well, in order to do that, let's read our procedure. I bet the next step is write the equations. Let's see. We listed our crap that we know and don't know. Next up is list our equations. And then notice we got to reread and make sure we're doing the right thing. So in this case, I'll write them over here. And I know this seems silly at first. If I were you, I would actually have a piece of paper out, and every time you do this problem, write all this stuff down. And even if you think, I don't need to do this for this easy problem, get in the habit now. And then what will happen is you'll have it locked in on test day where you just go and write it all out, and you won't be making mistakes like forgetting the 1/2 or forgetting the squared. So yeah, just please get in the habit of actually writing out everything, even if it seems stupid at first, okay? Can you guys even read this today? Is it too small here? I have no idea.
It's fine.
Okay, thanks. Now I'm going to leave a little bit of space here. So if I were you, I would maybe leave like a couple lines of blank space in between the equations. And if you're wondering where I'm getting these, it was from the bottom of page 21. So all I'm doing is I'm getting or you could look on the back of your book, right? I'm just writing these equations off the back of the book, these kinematics equations right here, okay? Couple lines of space. And I'm trying to keep the subscripts, even though we don't really need them right now. But when we go to chapter 4, it'll be nice if we're in that habit of always writing the subscripts, okay? That way we could tell the difference between an X equation for horizontal motion and a Y equation for vertical motion. All right. Now, the next step of the strategy is probably reread because I've forgotten what the heck we're trying to do. Yeah, bullet 6. We got our equations done in 5. Now we got to reread. So I'm going to do that too. I've already forgotten what we're trying to do. Time. We're looking for time. So the first part is this. So that's why sometimes, even though it's stupid, sometimes this WTF just reminds you, what is the goal? Keep your eye on the prize. What to find. So now, this is a little extra trick I like to do. And if you don't like it, that's fine. What I like to do is before I plug in any numbers, before I do any algebra, I want to think which of these equations is going to work for me. Now, you don't have to do it exactly like me, but this might help you a little bit, especially when you're starting, okay? Let me get this cable. It's kind of doing some weird stuff here. There we go. All right, so in this case, let's just go through and mark the things that we know. Delta X is known. So I'm putting a check mark, which means that's something I've got. Check, I got it. V initial X, I know that. V final X. Let's make that green just so it stands out, okay? So V final X, got it. Got it. Huh. All right, so in this case, and these two things I don't know. So both of these things I don't know. That's not looking good. Not looking good. Hey, so what do I think here? I'm like, you know what? This equation, I could work through this and get the acceleration pretty quickly. Why? Because it's the only unknown in that equation. So I would probably start here. And actually, is that part B? Look at that. So in this case, I read the question again and I'm like, huh, it's actually easier to do part B before part A. So what I could do is this: solve for this equation, get A algebraically, solve this equation for T algebraically, then shove in this result into that result. And I got to tell you, this one looks the worst because it looks like it's a quadratic and it's like you could use it, but you might have to use the quadratic formula or something. And that's not the end of the world. I mean, I would not shy away from solving a problem just because there's the quadratic formula in it. But here, this just seems so much easier to me. So let's go ahead and work this one out right here. All right. And I'm going to pause because this is probably more important than doing the algebra. If you do enough practice, the algebra is not physics. You will get good at that. This is the part where you have to make sure you can draw a picture, make sure you understand what you know, and document what you're looking for, and make sure you clearly figure out which strategy to approach it with. If you could do that, these problems are all the same. If you can't do that, you're miserable. So before we go on, I'm going to pause, see if there's questions. Is this making some sense? Any sense at all?
So which one was it that you were saying that we may have to use a quadratic formula for?
Well, I look at this one. This one has a t squared up here. The equation that had t squared in it. I don't know if I need a quadratic formula, but it's like none of the rest of them have squares in it. That makes it feel easier to me. I don't know if it is, but yeah. Is that good, Dom?
Yeah.
Other questions? Right off. Oh, go for it, Edgar.
How do you know which equations to choose?
Every problem is different. So the only thing that I could tell you, Edgar, this is how I know. I write this, I write those, and I look for what do I know and what do I not know. I let that tell me which equation to choose. So again, this whole procedure of drawing a picture, listing this, writing the equations, and finding out which things are unknown in those equations, that's what tells me. And I look for an equation where there's only one unknown. Because this one's too hard to solve. This one's too hard to solve. I have two things, but only one equation. Is that kind of good, Edgar?
I was asking more why you chose those three.
Oh, because the problem said constant acceleration. If you have a constant acceleration, these equations are valid.
Okay.
And so that's a little piece of physics. We know that these are called the constant acceleration kinematics equations. Good question, Edgar. If you know the question is constant acceleration, that's what tells me to write down these three. Is that good?
Yeah, that's great. Thank you.
Nice. Good question. Good.
So is there more formulas that we're going to use in the future for like?
There are 5 of these actually. And, but it turns out you can solve any problem with only 3 of them. I know this from experience because all these problems, if it's going to be solvable, there's always going to be 3 things you know and 2 things you don't. And out of those, usually you have 2 equations that are needed to solve the problem, and then 1 that can be used to check. And so it's almost like an error checking code if you're into that.
5 equations for constant acceleration?
Yeah, they're like, so look at the 5 variables, right? there's 5 equations that you can find on the internet
Oh.
sometimes, and each equation has something special, right? Each
Mm.
equation has one of the variables missing. So what you could do is you could use these equations, and like in this case, see how this has got V initial in it? You could
Yeah.
actually use this equation right here to solve for V initial, plug it into there, and then you'd have an equation that doesn't have V initial in it.
Mhm.
Or yeah, so there's probably an equation. So we have an equation that doesn't have time. Here we have an equation that doesn't have X, et cetera, et cetera, et cetera.
All right.
So you could actually have an equation that doesn't have A in it, and that's a fancy version of distance equals average rate times time.
So will the other formulas become like needed later
No.
on? No?
Like I said, you can make them in one line of algebra from these, or
Okay.
2 lines of algebra. And so I call these the big 3. And so you don't really need 3, but excuse me, it doesn't matter which 3 you call the big 3, but for me, these are the 3 that I use most often.
Okay.
If you want to learn those other ones, if you want to memorize them, that's fine with me. There's no harm in that. You have more tools. But personally, I don't like memorizing things. So I just have these 3 and I just rock with them all the time. And I've been doing it 20 years and they've solved every problem so far. So it seems to be working.
All right. Cool.
Yeah. I call these the big 3. Yeah. my 3 favorite. This one is really good to know for things like max height, or anytime you have a velocity that goes to 0, either the initial or the final. This one can sometimes be really useful because look how easy it becomes. And yeah, this one's really good for time if you know the distance usually, but in this particular case, we see, oh, because you don't know the acceleration, this one's slightly better.
Isn't
Good
there
questions.
like not a lot of things like in physics that have constant acceleration?
Say again.
Isn't there like not a lot of things in physics that have constant acceleration?
Almost nothing in life has constant acceleration.
Yeah.
But it's really easy to write a computer code that splits up the time into tiny little segments where acceleration is constant. And then what you've done is you could take any real life phenomenon and split it into small constant acceleration problems, as long as the computer does all the math for you, which means you have to understand the algebra so you know how to code the computer to tell it to do 10,000 calculations of this. I've had Jay has probably done 700,000 kinematics equation problems because I know that she's done a few computer codes with animation, and they each do hundreds of thousands of calculations, right? Or tens of thousands. So yeah, if you get good at this, you could actually use these in non-constant acceleration applications if you're smart with how you split up the problem, just like calculus.
Okay.
Is that cool?
Yeah.
I think it's cool anyway.
That's
Yeah.
really
So
cool.
all right. Good questions. Others? Let's go ahead and rock this one out then, okay? So I've run out of room. What I'm going to use is I'm going to do this. I just need space, right? So I think we said this top equation we don't really need. So I'm going to work with these. I'm going to rewrite them up here. Oh, here's another trick, everybody. This is good to know. So I know you're tired. Maybe I'm babbling too much. Please pay attention right now. The first thing you want to do is plug in anything in here that's a 0 before you do the algebra. So before you do algebra, geez, come on, make your life easier. Wasn't this equal to 0? That's a lot easier than doing algebra with that thing in there all day. And this was also equal to 0, right? Oh my gosh, that makes the algebra so much easier. So if you have any numbers that are 0, plug those in right away. Then do the algebra. So just rewriting this up here, I think what I see is I get this one says 0 equals V initial X plus A sub X T. And we're not going to plug in the numbers till the end. This one, I get 0 equals V initial X squared plus 2 A sub X delta X. And now I can erase those. That's just those equations. All right. So by plugging in the zeros, the algebra gets really easy. I can look at this equation and say, well, this one says, what are we looking for in the second one? I don't know, time, right? Eventually we want to know the time. So let's solve this equation for time. Well, that says negative V initial X is equal to a sub xt, which then becomes, again, I'm going to divide and then flip them. That minus sign is really important. Take a look at this. We're going to expect that the time should equal minus the initial velocity over the acceleration. Somebody, I forget who it was, already said we expect acceleration to be a negative number. So when I plug in a negative number here, that'll cancel this minus sign, and I should get a positive number for time. That's why this is important. We do not want to hide our minus signs. Never just magically make a minus sign disappear. If you do that, it will just eventually cause failure, okay? Meaning you're going to fail quizzes and fail stuff. So, all right, what else can I do? How could I check if this equation is right before I go on and get the other stuff? Check the what?
Units.
Units. Well, what are the units on top?
Meters
Meters,
over second.
right? And then on bottom, what are the units?
Meters over second squared.
So then what I'm going to do is not overthink it. I'm going to let the paper do the work. Do not try to do this in your head. Trust me, I still make mistakes when I try to do everything in my head. I'm just going to write it out. I'm going to multiply by the reciprocal. That cancels out the seconds here on bottom, meters. Notice the meters drop out. The second, I get seconds. Isn't that a unit of time? That's how we use chapter 1 on a daily basis. Checking the units. I may have done that quickly. I'm going to zoom in just to make sure you could see that. Again, I took this equation, I did some algebra, and then I checked the units to make sure I didn't flip something. That doesn't guarantee I got it right, but it's at least one way to check it. So all the meters per second dropped out. I ended up with units of seconds. That's a time. I'm going to pause. Everybody, hopefully you're good on that. And I've run out of room. So that's that. We still have not solved the problem. WTF is time, but I don't know the acceleration yet. So I'm going to go over here and get it. All right. So again, I'm going to solve this algebraically. Well, what are we looking for? A sub x. So maybe I'll bring that over here. Okay. Now let's see. I could divide this. I could divide each side. Oops. I want to solve for a sub x. And it's customary to bring the minus signs out front. Now I have a question for you. You can see I said a sub x equals negative v initial x squared over 2 delta x. The question is this: does this minus sign get canceled by that squared?
No.
No. And now what you've got to learn in a physics class, a lot of times people are going to write this, myself included, and eventually your friends and colleagues, they will write negative v initial x squared over 2 delta x because it's neater. So you'll see this sometimes brought up into here. You need to know that this right here is the same thing as negative, then do PEMDAS, right? So that's v initial x squared. So the idea is you do the squaring first, then you make it negative. Now, wait a minute. What are some ways we could check this before we plug it in? What's one thing I could check? Somebody that maybe hasn't spoken up today, feeling brave. I appreciate it. It's okay to be wrong. So somebody that hasn't unmuted today, maybe take a chance. What do you think? What's one way we could check that? And those of you that usually unmute, just try to be patient. Wait them out.
Oh, is it It's units. We got to check the units.
Yeah, we could check the units. Oh, somebody put it in the chat. Oh, okay. Oh, whoops. That's probably an old one from Jay. My bad. Okay. Yeah, we could check the units. Somebody other than Dom, what's another way we could check it? What
We
should the,
can-
oh, go ahead. Yeah, go for it, Erica. Sorry.
No, now I
Oh.
feel self-conscious.
Oh, yeah, yeah. It's super goofy. And right. So this is when it's nice to be in face to face, right? Because usually you have a neighbor and you guys can whisper and nobody hears you, right? So okay, so you know that's fine. I don't want to put you on the spot anymore. My bad. I was thinking about this minus sign. So maybe think to yourself, is this minus sign a good idea? Let's think. So we could check the units. You could also check the sign of an answer. That's what we did up here. We checked time should be a positive number. We expect acceleration should be a negative number. So let's see. If I put this in, that's positive. Is delta x positive? Yes. So I expect all this crap here is going to be positive, and then I'll get a negative number for acceleration, which should give me a positive number for time. I'm feeling good, and I'm on the wrong view. Let me do that again. Sorry about that live stream. My bad. So here we get to plug in numbers here. This is positive, positive, positive. I should get a negative number for acceleration, which then means I'll get a positive number for time. The units are going to be, let's check them, meters per second. I'm going to square that, squared, squared. And then I'm going to divide that by meters, right? So I'm going to multiply by the reciprocal. Do not try to do it in your head. Meters per second squared, that is the correct unit that we expect for acceleration. So hopefully this makes you feel a little bit better about why we were doing chapter 1. We use this stupid unit check all the time. It's not the be all end all, but it's one way to make sure you didn't flip something upside down. That's it. Right? And boy, it's helped me many, many, many times. And the few times I don't do it, I'm like, why didn't I check it? I see it all the time on tests, right? People forgot to check the units and then they flipped something upside down and missed the question. So, all right. So let's go ahead and finish this puppy out. Notice we still have not plugged in any of the numbers. It probably feels uncomfortable to you at first because you're used to just shoving stuff in your calculator. If you get used to it, you will learn to hate plugging in numbers. Just ask Jay, who has to take these tests with all these numbers in it, and they're all just hating life right now. It's so much easier with algebra once you get used to it. Okay, so all right, I know the acceleration. I can plug that into here. Let's just do it. So again, what is my goal? I just figured out this thing here, this purple flowery thing here, and that is this. And what I want to do is I want to shove that in right here and make an algebraic expression for the time rather than plugging in the numbers. Why? Because I can check it before I plug in the numbers and make sure I didn't screw up. It's one slight advantage. So I get a negative v initial x divided by all that junk. I get that. Lo and behold, this is going to cancel. I can multiply by the reciprocal and clean it up, but I've totally run out of room, and I'll check that question in the chat. Yeah. Hey, I'm with you, Jay. I'm with you, man. All right. Numbers are a lot harder. I screw up when I plug in numbers too. So, all right. So I'm going to rewrite this down here. I'm just kind of running out of room. I'm going to multiply by the reciprocal. I'm going to let the paper do the work so I don't screw it up. I see in the basement. Let's get this up closer and maybe angle down so you can see it better. So that's just a continuation. I'm just continuing this down here. Sorry. Let's see. The bottom should cancel out. And now one of these should cancel out. What's something I should check right away? Somebody other than Dom. Every time you get an algebraic answer, check the
Units.
2 has no units. It's just a number. This is meters over meters per second. Times that by seconds over meters. Seconds over meters. Seconds. Looking good. That just makes sure we didn't flip something. Now, look how easy this is to plug in numbers. We did all this work without having to write down 5, 6, 7 sig figs all the time, right? Think about this. If you have to type this into Canvas, oh my gosh, you would not want to keep track of 6, 7 digits and then worry about subtraction. Oh, do I need to worry? Because we did it this way, we don't need to worry about sig fig rules and keeping 10 digits and worried about storing numbers in my calculator. So freaking fast. All right. All right. So now, and if the distance was different, what if I'm an engineer? What if I need to play around with this? And maybe you want to take this equation here, right? You say, what's the maximum legal speed I want to keep somebody from dying? Because they're going to hit these barrels and try not to die, right? We're going to try not to kill somebody. So figure out the maximum speed. That tells you how big the distance needs to be. Otherwise, they'll kill themselves when they crash. So these are design elements. You could try out different speeds, different distances, blah, blah, blah. And you could design different amounts of sand barrels and blah, blah, and check it out. So, all right, enough on why you do algebra. I think I've emphasized that enough. And so at this point, let's just go look at the numbers and see. There was the plain one. Okay, so I know I took a long time to do all this, but there's some information. Looks like what I did was part A first. So I did it a little bit differently here, but it's the same procedure and you should get the same answers. So that looks cool. And yeah, so there's the numbers if you need them for AX. And it looks like this is the time. So that looks like part A and B or something. All right. Let's check here with the question. Oh, sorry. I didn't screen share. My bad. Sorry about that. All right, so in this one, you could figure out these two things. So let's go take a look at that in the solutions here. So there's the time. Maybe I didn't put it in the perfect order, but yeah. All right, so that's cool. And then let's go back and read the next part of the question. You could do the problem again if there were no barrels present. And this is one more huge advantage of doing this algebraically. If you want to compare, well, all you need to do to change this one is change the values of delta x, and you can get a new value of acceleration and figure out how much brain damage you'll get. Yeah. Finally, I do want to point this out. You've probably heard about G's. How many G's are you experiencing? All that means is take your value for acceleration, divide it by G, and this would be the number of G's. So for example, if you had 8.25 meters per second squared, that's the same thing as 0.842 G's. It's just the amount of G's you experience in terms of acceleration, where 1 G is 9.8 meters per second squared. All right, so let's call that good for a second. That was a long problem. They won't always be this long. Yeah, I'm going to check. Any questions about any of that? Making some sense? All right. I'll let you guys try to do 2.1.34 on your, oh yeah. So Ruth, here's how you get G's. Take your acceleration. Okay, so I need to erase this. I'm running out of room. It's written somewhere in that workbook problem in one of those long-winded questions, but basically, if you have an acceleration of say like 3.5 meters per second squared, you could just take that and divide it by G on both sides, which is 9.8 meters per second squared, and you get a number. That's how you get the G's. So 3.5 divided by 9.8 is 0.36-ish. So that means my acceleration is essentially 0.36 G's. That's how you get your G's. Is that good on that? Yep. Yeah. And so it's basically G is a unit of acceleration. So think of it like eggs. You could talk about how many dozens of eggs you have, and that gives you a total number of eggs. So if I said you had 3 dozen eggs, you know you have 36, right? If I say you have 0.36 Gs, well, that's just 0.36 times G gives you your acceleration. Same kind of thing. Or moles of atoms, right? A mole is just a really big, it's like a dozen on steroids, right? It's a really big dozen. All right. That's weird. Yeah, anyways. Okay. All right, let's go to the next page. So I'm looking at page 24. Let me do a quick screen share. Oh yeah, this one. You guys should do this one at home after this class. And I think you will see it gets tricky. One of the things that you might do is use the solution while you follow along if you get lost. And what I did was I described this part of the problem with blue symbols. And then you have another part of the problem. You got to start over. You do it with red. Another thing you could do is you could say everything on this side has a subscript 2 to keep track of it, whereas everything on this side has a subscript 1 because it's the first stage. And so you could see if you can, what you should see is it gets more and more important to learn how to neatly organize your work, how to neatly draw your pictures, and to keep all your subscripts straight. So I'm going to let you try that at home, follow along with the solutions, and ask questions next time. Okay, so there's that. Whoops. Let's go down here. So now here's the idea for this page, 24. Now we're kind of getting closer to real life physics problems here. So we're going to try and do purely algebraic problems. And I'll be honest with you, this is the most interesting part. This type of solution could be used to create computer simulations. That's why I like that. And there's all these other reasons that we've discussed already. So let's get to it and find out how these problems look a little different. Students are usually not used to this when they're first doing a physics class. So I'm looking at 2.2. I'm going to draw that up. You can read it yourself. Okay. We'll adjust the board in a minute. So I'm trying to draw, label, and you could do it yourself and not watch my screen and then see if we do the same kind of picture here, okay? Just still reading, still reading. Okay. So that's how long it takes me to just read it carefully. So notice, even though I wrote the damn thing, it still takes me quite a while to read it carefully. And this is what I got out of that. This is the stuff that I wrote down on my page. You could maybe check and see if this is the same stuff you wrote. And actually, I need to put one more thing in the picture here. Right? So these are the things that I drew. Notice this problem has chosen to use a rotated coordinate system. You may not like that, but you'd better get used to it. It turns out a huge number of physics problems can actually be made easier if you have a rotated coordinate system. So you just got to trust me on that. Albert Einstein, this was one of the postulates of special relativity. Your coordinate system should not matter for the final answers. Like how long it takes to get down the ramp should not matter whether you call this way positive, that way positive, this way. The time to get down the ramp is the time to get down the ramp. The coordinate system is a human construct from our minds, man. Trip out on that. So yeah, it shouldn't matter what we do with this. We should still get the same kind of answers when we think about real physical quantities like time or speed. All right. So that's what allows us to rotate this, and it just makes it easier. Now, this is actually a 1D motion problem where things are going this way. That's so much easier than dealing with 2D motion. All right, it was released from rest. There's no friction. The ramp length is L. I labeled that. I got this. So that's what makes me think. The next step, list. List your crap. Okay. In this case, be careful. I said this way is down. Or sorry, this way is positive. Look at that. My finger lines up with the arrow. So what is delta x? Is it L or is it negative L according to this picture? It's going to go down the ramp. It should be positive L. Now, something that weirds out students at first, this is known. You're supposed to assume this is a known quantity. Why? Because nothing in the problem statement indicates otherwise. I want to show you something here. Whoops. Oh, crap. Come on. What happened? Okay, sorry, my Zoom locked up there for a sec. My bad. Hopefully, can anybody hear me right now? Just check.
Yeah.
Okay, thanks. I appreciate it. Sorry, Zoom locked up. Okay. In this case, it says assume this ramp is L. When it tells you that, you have to assume that's a known, that's a given. All right. Theta, we're going to assume that's a given because it's shown in the picture. G, that's a number that we know. We're going to assume those things are known. Okay. So that's the deal. We have to assume that. And notice in this problem, we're going to be trying to get answers in terms of these things. Look at this. It says it reaches the bottom in time t. There's another known. So you are supposed to know that L, G, theta, and t are known quantities, even though it doesn't explicitly tell you that. All right. That's usually a confusing part for students. So that's one major difference when you see a physics word problem. The letters that are given in the problem statement are knowns, and the letters that aren't given are unknowns. Okay, so let's get back up to this. Lost a marker here. Appreciate your patience, everybody. Zoom class is no fun. All right, let's keep rocking. V initial x. That's 0. Got it. V final x. Nothing in the problem told me that. A sub x. Aha, that's g sine theta. Time, was that given to us or not? What do you think?
No, is that what we're finding?
Read carefully part A. If you, it's not given in the top problem statement, but read the sentence in part A. It is given. It says, determine the angle required to reach the bottom in turn. Oh, we're supposed to get theta. Oh, crap. There's a typo there, isn't there? But yeah, T is given, but theta is not given. We can't get theta in terms of theta. Let me show you what I mean on that typo here. Sorry. I must have changed that question at some point. Take a look. We're supposed to determine the angle. That's a sign that the angle is not known. So what I'm saying here is this should not be here. I got to fix that up. I need to take that out. My bad. Page 24. I'll fix that soon enough. Moral of the story, never write a book. It's endless hell. Okay. All right, but the idea here is T was given, and this is the sign. It says it reached the bottom in time T. That's what tells me it was given. This says determine the angle. That's what tells me theta is not known. So apologies there. Hopefully that made some sense. So this is an unknown right here. This is a known. We know G. All right. Next step, write your equations. Leave a little space so we can check it. Leave at least a couple of lines. Couple of lines. There's our equations. So now we don't even need the picture. We could just focus on this. What are we looking for? Theta. Which one of these variables has theta in it? A. So we're going to go through. This is basically WTF. We're looking for the acceleration. If we can get the acceleration, we know what G is. We should be able to find theta. So what could we do? Let's see. This is what we're looking for. Technically, L is a known, right? L is one of these things that we were told at the beginning. So I'll check that off. Time is known. And then V initial is known. And in fact, that's a special known. That goes to 0. Finally, V final is unknown. So looking at this one, this seems like a bad place to start. This seems like a bad place to start. Why? I have two unknowns. Could you do it? Absolutely. You could take this, plug it into there, and then you'd have one equation for A. But look, isn't that basically what this is already? We know delta X. So this one seems like the way to go. All right. I'm going to go ahead and rock that out. We've already plugged in the things that are equal to 0. That's the first step. So now I can rewrite. You could plug in these variables right now if you want, or you could do the algebra first. Why don't we just do the algebra first this time? So we're looking for a sub x. So that's going to be let me just pause and make sure. I'm going to multiply by 2. On each side. Divide by t squared. Yeah. I could check the units, meters over second squared. Looks good. And then I think we have everything we need. So now we could just plug this information in. Now I've done some algebra. I'm going to start plugging in the letters that are known. All right. So now we do this, and I'm just going to flip this side because it drives me crazy to have it that way. This is going to be 2. X was L over t squared. I guess we could write that a little neater. Have we solved the problem? Classic thing, keep your eye on the prize. What are we looking for? Theta. We have not solved for WTF yet. We have not finished. I need to plug this in too. So I'm running out of room. So I got to move this over there, do an inverse sine. Running out of room. I guess I better do it over here. Can barely fit in this. That gives me the angle. Done. That is what was asked for. How should I check this? What should you always check? Somebody other than Dom.
Units?
Units. Now think, this one's a little bit weird. We haven't talked a ton about this, but angles should have no units. Also, functions, the arguments of functions should have no units. If you want to talk about trig, you should say, wait, isn't this degrees? It turns out the calculus unit would be radians, which is equivalent to no units. I could prove that to you another time, but just for right now, let's say this is supposed to have no units. Whatever's inside should have no units. Well, look at this. Meters per second squared times second squared would be meters. Meters over meters, it works out. I've just run out of room to check that there. But so this has no units, and that's correct. Sometimes you do have no units in a problem. That should be true for these functions like this. So that's an idea of how you could get started on that one. Let me pause for questions here. So that's kind of the whole problem. Oh, go ahead. What's up?
So is the equation the answer?
Yeah.
Oh, okay.
Yeah, isn't that cool? or
Mm,
weird?
I would say weird. I guess I'm just so used to solving and putting in
Yeah.
stuff. But okay.
So
Cool.
this is what's different about this. So imagine if you had this on a Canvas quiz. It's really hard to do this on a Canvas quiz because I literally have to make up every possible function that you could screw up on to put in as a multiple choice answer. And I've done that for some, and it takes forever. So basically, there's going to be some questions where you say, what's the correct algebra statement at the end? Why is this important? Remember, the algebra is what you then take and shove into a computer program to do the hard work for you. So this is why it's crucial to learn this weird style of doing it all letters, all algebra with no, yeah. Yep. Cool. Imagine if you then had this running in Python, you could put in a little slider and tell people what value of L, what value of G, what value of T, put in a bunch of math in the computer code, and it would spit out angles, and it could make plots for you and do all kinds of cool stuff. So, yep. Other questions? That was a good one, Erica. Remember, you could always harass Jay too and ask her questions, right? All right. So let's see. What else do we got? I think we're about ready to do a vertical problem. So I'll say this. Let me show you a screen share. I should be clear. When I say harass Jay, I don't mean harass her. I mean ask her questions. When I tell people to ask me questions, I say harass me. So yeah, anyways, all right. This one right here will get you. Make sure you do this whole page, everybody. So by the end of the weekend, you should definitely have up to 2.4 done. And that includes all the different 2.1s. Don't you love that sneaky trick of having multiple 2.1s? Oh, come on. It's only up to 2.4. 10 problems later. Okay. But so, yeah, you could do those. You could do these problems as well. 2.5 is a good one. There's a plot. You could see, how do you generate these plots? You use those algebraic equations. These ones we'll maybe talk about in a little while. Those are pretty cool. All of those you could do. This is where I kind of wanted to get to next, 2.8. So let me check what the chat was there. Yeah, I know. Okay, so now let's take a look at this one. I want to talk about free fall, what this word means, and do a quick free fall demonstration. And I think there's a video linked somewhere here, and I'll show it to you if we have time at the end, maybe. Yeah, I don't have all my demos here, but let's talk about 2.8 really quick. And this is page 27 if you've got it. So free fall means gravity is the only force acting on an object. So free fall means gravity is the only force acting on an object. So if I drop this thing, you might say, well, what do you think? Is that free fall? What do you guys think?
No.
Why not?
There's air resistance.
Yes. Now, what if I do this full coffee cup and drop it? I'm not going to. But if I drop, yeah, now let's party. Now, what if I drop this empty coffee cup? Whoa, man, I don't trust my left hand at all. All right, so in that case, what do you think? Is it free fall? Is my computer locked up?
No, I'm just not sure.
Oh, yeah. Okay, so is there still air resistance?
Yes.
Yes. Is air resistance negligible? Probably.
Yes.
Yeah. So dropping an eraser, which is basically it's very light piece of foam, air resistance matters a lot for this case. I'd agree with you. This is not really free fall, but dropping a coffee mug, there's so little air resistance. I would say it's approximately free fall. So just to go into this, so the idea here is we are going to assume problems are free fall, even if they're like this eraser. And what does that mean? It means our answers will not give exact answers. They might give us a rough idea of how things behave in the real world. Almost nothing in the real world is in free fall. An example would be the moon. How much air resistance is there in space? Not much. 1 molecule per cubic meter. The moon is being acted upon by gravity. That's a free fall problem. It's falling towards the earth. We're just lucky that it never hits us because it's moving fast enough. Anyways. What if you have a rock and you drop it from a small building? Not much air resistance. It's free fall. If you drop it from a large building, then you might get some air resistance down at the bottom. A skydiver. The first 2-3 seconds are probably free fall. After that, air resistance gets large, and eventually you hit terminal velocity. So we see that there's times where free fall is a good model and times where it's not. How about a plane flying? It's not going to fly if you don't have air resistance, right? That causes lift as well. So yeah, we know that a plane flying it's not a free fall problem. All right, anyways, just moral of the story, free fall, we're going to use it. We're probably going to assume everything has no air resistance because it's too hard to use air resistance until we get to computer coding. So for now, let's just leave it at that. We're going to do a lot of free. Let's see if there's anything else I missed in here. That was this stuff here. So the beginning of a rocket launch is not a free fall problem, right? There's the thrusters pushing up against gravity pulling down. Once it gets into space and the rocket thrusters are off, you could argue it is a free fall problem. So not free fall, probably not free fall, but we treat it that way anyways. Not free fall. This is actually free fall, but too hard to do until we get to a later chapter. And you could actually see what happens. I'll try and find this video for you. And I can't remember where I put the link. I may have put it in the solution. But if you look, you could actually do this experiment in a lab where you take a coin and a feather, and they will literally, you could videotape them and watch them, and they literally fall at exactly the same rate if you get all the air out of there. And I'll put that in at the very last thing right after we stop the chat, okay? Or stop the session. I do want to get to a problem here. Okay, this one's a fun one. 2.10, you could read this on your own. Blah, 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 blah. This one, 2.13. This might be the longest problem I've ever written. Parts A through M. It's going to take all morning. Ha ha. Okay, let's get this cleared up here. We're going to look at this one. Notice I didn't draw the picture this time. So you've got the answers in your workbook. Try it before you read the answers and find out what you screwed up. Try to make this a little bit interactive with yourself. So you think, this is what I think you should draw. And then go see what I drew and see if it's approximately the same thing, that kind of thing. I'm going to let you guys get to it. So this is 2.13. Okay, and so I'm going to draw it myself, and then we'll try and look at it. When you throw a ball upwards, it is in free fall. After it leaves your hand doesn't exert any force on it. I got you. Air resistance is negligible. Okay. That's what my picture looks like. Hopefully you drew something, you might not be perfect. One of the things that I've discovered is rather than try and go perfectly straight up and down, you just draw a little bit of space there so you can label things better, right? So it goes up here to max height. That's the first things that encountered when I thought about it. I'm going to go back and read more of the problem. So that was part A, sketch the picture. What initial velocity? I'm immediately going to go to my list of crap, okay? Oh, we're going upwards, so I'm not going to use X anymore. I'm going to use Y, and I guess I'm assuming this. This is the X direction, and this is the Y direction, right? That's usually what people think like. So now instead of delta X's and V initial X's, we're doing delta Y's. Okay, so you've probably had a second to look at it. Let's focus right here. This part, I really want you to understand this one, okay? So please listen, even if you're tired and ready to go. Delta Y, what is the change as we go upwards? So it says, and what are we trying to get? Part B says, what initial speed to reach that max height? I think that was the question, right? Where was it? Come on. Yes, that's what was asked. So in this case, what is delta Y? What do you think? Take a chance. It's okay. The more interactive you are, the more you learn. So it's okay to like guess and be wrong. Those students usually end up getting A's on the test because they've made their mistakes in class instead of on paper. What's
So
delta?
4 meters.
4. Excellent. Do you agree that the distance up to the top is 4.0 meters? This is right. It's neither one of the numbers that was given, but it relates to them. The change in Y goes from 2 up to 6. Excellent. Nice job. Positive or negative in this case? Did it go up or down?
It's positive. It went up.
Yep. Okay. What's V initial Y? Do we know that or not?
2 meters.
This means initial velocity. Meters doesn't make sense for that. Do you agree?
Right. Yeah.
So that's a way you would probably check that as soon as you write it down. So that's good. So in fact, that is what we're looking for, right? Initial speed relates to initial velocity. That's WTF. I appreciate that effort there. All right. How about what's the velocity up at the top? This is a tough one.
0.
Yeah, why do you say 0? What was your thought process, just so I know?
Because like as it's leaving your hand, it starts decreasing in acceleration, and then after that, it starts going down. So it has to
Absolutely.
like balance out.
Absolutely. As it's positive velocity getting smaller. And then do you agree when it's here, the velocity is negative? So at some point it has to go from plus to minus. That's the very, very top. Okay, so here, the velocity at the top is 0. All right, everybody. What's the acceleration at the top? Somebody else. Erica spoke up. I don't know who that last person was, but thank you, both of you. What's the acceleration at the top? What do you think?
Is that 0 also?
No. And the most common thought is it should be. Let me ask you this. What does acceleration mean? Acceleration means change in velocity, right? Change in velocity over change in time. If the velocity at the top is 0 and the acceleration is 0, the ball would go up to the top, magically float, and never come down. That doesn't occur in the real world, right? Because if it had 0 velocity and no change, it would just sit there forever. We know from experience, the velocity changes from 0 to being a negative number. So it's not 0. That was a great thought. Okay.
Isn't it something that we'd have to like calculate? Like,
Nope.
Wouldn't it be negative? But like, I don't know like exactly what the number would be.
It is negative.
Because I know the velocity is the acceleration is negative the whole time, right? Even though the velocity is positive. And then
Yep. It's a G thing.
Oh.
It's G. Negative G. The acceleration is down. So remember I told you G a couple days ago? I was setting you up for this trick question. All right. Oh, that's sneaky Jorstead. It's accelerating in free fall at rate G downwards. Be careful here. G is 9.8, always positive. Always positive. G, where is it? Right there. Always positive. The direction is downwards. This is the magnitude. That's the direction. Now you see why we do chapter 3 first. Okay, so here we go. We got G. We got 9.8 meters per second squared. And it's negative. This is from the arrowhead. This is from the G. It's equal to negative G. It is not G. It is not G. Hey, it's not G. All right. And then the time, take a guess. How many unknowns do we always have in a chart of 5? 2. And I'll get the question from the chat in just a sec. That's right. Free fall. And so this is constant acceleration. Absolutely, right? G is a constant. Look at this number. It's a constant. This is a constant acceleration kinematics equation as long as we ignore air resistance. If you include air resistance, it's very complicated. We can't do that problem yet. So what we do is we do everything as if it's constant acceleration. The magnitude is G. The direction is negative. All right. And so from here, same old problem. List your crap, write some stuff, solve for something. Got it? Now, I want to point out something here again. So definitely ask any questions right now. This is the hard part, right? Once you get this, you write your equations and you solve for something. That's math. This is the physics part. Look at that lovely physics hand wave there. All right. Let's see what the chat is here. Okay, good. And I know we're running out of time here, but I do want to point out one last thing. I want to do one last thing. Okay, so you could do all this crap, blah, blah, blah. Oh, look at this. This one talks about max height. I do want to point this out. Look at part D. This is the entire time of flight. What we see here is that there's many different types of questions you could ask about this same problem. Okay. These first two, we just did the picture for. Well, the entire time, how would I handle this? I would start all over and I would make a new list of knowns and unknowns. And so for part D, I want to show you one last thing here. This is the last little trick that screws people up sometimes. So let's do this. Stay focused. If we were talking about the entire flight from here to impact, what would be the change in y? If I go from this point to that point, what's delta y?
-2 meters.
-2. And the negative, people are like, the distance is 2, but the displacement. Remember that this delta y, even though there's no vector here, has what implied on it? There's a secret j hat on all of these things. Oh, sorry, I cut you off. My bad. Sorry, I stole your thunder there. The idea here is there's a j hat hidden on all of these because they're in the y direction. If we were moving in the x, everything had an implied I hat. So really, this is vertical displacement. It is not distance. All right. That problem is really good for getting, I tried to find every possible trick I could. I looked at every single mistake students have made over the 20 years I've been doing this, and I shoved them all into one problem. And so you can kind of, and it's got numbers in it. So I don't usually give problems with numbers. So it's a great first problem for you to do at home. So even though this sounds crazy, if you could finish all the problems up to 2.13 by the next class period, you are going to rock this. If you don't have time to get that done, it's just going to balloon and get out of control. So I would really, this is the time to make a stand on chapter 2. If you can get this done up to 213, the rest of it you'll have next weekend to catch up. But please, please, please get to 213 by next class period, and including that one. And if you have to follow along with the solutions once in a while, do it. But remember, start to wean yourself off the solutions. Try to do it without, check. Try to do it without, check. If you're completely lost, do that whole problem with the solutions. Then the next problem, try to do it without and check. And eventually you should get to the point where you don't need the solutions. Otherwise, you're lost on quiz day. Let's stop that live stream, right? I appreciate the extra time today. You guys are troopers. Whoops.